In this video, we're going to be doing a second example problem involving a free-falling projectile moving in 2 dimensions. We're going to be using these equations here, the kinematic equations for a free-falling projectile moving in 2 dimensions. These were developed earlier. And we're also going to be using this kinematics procedure that we have used in all of our previous kinematics examples. So let's look at the problem. We're going to imagine that we are a besieging army in the Middle Ages, and we are going to set up our catapults so as to attack the castle, which is behind the castle wall back here. We're going to take our payloads to put them in the catapult and try and launch these over the castle wall with the idea that maybe whatever we're launching here gets behind the castle wall and causes problems to the people back here who are defending the castle. Maybe this is something on fire, maybe this is biological weapons. But anyways, we want to get this stuff over the castle wall. However, we are also worried that maybe there are archers up here trying to shoot their arrows at us. And because of that, we want to get our catapult as far from the castle wall as possible. The way we can get our catapult as far from the castle wall as possible is to aim our shot so that the shot just barely clears the castle wall, right? If we were closer, then our shots could make it over the castle wall with some clearance, but we don't want that. We want to get far away and have our payloads just barely clear the castle wall. Okay, let's get to the problem here. So we have our catapult. The catapult is launching, let's say they're rocks, at 35 meters per second. The initial velocity is directed 50 degrees above the horizontal, and we are shooting at a castle wall 30 meters tall. As I suggested before, our first problem is going to be to try and figure out the maximum distance between the castle wall and the catapult such that the payload will go over the castle wall. And then just to get some more practice doing kinematics problems, we're going to find the maximum height of the rock. The maximum height of the payload is achieved over here. And by putting the maximum height of the payload over here, we have a bit more distance between us and the castle wall in here. Okay, and then finally, we're going to find the speed of the payload as it goes over the wall. Okay, so let's go to the handout. So step 1, draw a clear sketch illustrating the problem. I got started on a sketch. 2, draw a coordinate system. So here our coordinate system is X and Y axes. And I put the origin at the catapult here so that the entire process happens in the first quadrant, so we don't have to worry about making sign errors with negative X or Y coordinates. Okay, so that's our origin right there. Identify and number the moments of interest. So why don't you give this a shot? Pause the video, identify and number the moments of interest, and you can even go to step 4 where you put in all of the necessary kinematic variables. Okay, so there are 3 moments of interest here. Moment of interest 0 would be immediately after the launch. Right? Remember that we do not put a moment of interest during the launch, because during the launch we do not have free fall. The catapult is still acting on the payload. So we start looking at the process just after the launch. That'll be moment 0, and moment 1 will be at the maximum height. And then moment 2 will be when our payload clears the wall. Okay, now we're going to put in our kinematic variables. So this is a constant acceleration problem. So we want to put in variables to denote time, position, and velocity. Because this is a 2-dimensional problem, we need 2 variables to indicate position and 2 variables to indicate velocity, right? Because we have X direction and Y direction. Okay, so moment 0, let's put in at time 0. x0, y0, vx0, vy0. For moment one, we're going to have time one, x1, y1, vx1, vy1. And then for moment two, time two, x2, y2, vx2, vy2. Okay, the next step, let's put the acceleration in the figure somewhere. As usual with these free fall problems, the x acceleration is 0, the y acceleration is minus 9.8 meters per second squared. Okay, so the next step is to go through the figure and those kinematic variables whose values we already know without doing any computation, we want to put those in. However, this time we're going to do something a little bit different because we're going to get the initial x and y velocity by taking components of that velocity vector as we saw in the previous video. So let me just take that velocity vector v0, pull it over here, and then we will take x and y components. Okay, so here's our initial velocity vector v0. It makes a 50-degree angle with the horizontal. The statement of the problem says that the launch speed is 35 meters per second. So this is giving us the magnitude of the velocity vector. So I'm going to put in v0 for the magnitude of the velocity vector, 35 meters per second. And now we can take components. So this would be our initial x component of the velocity. This here, that would be our initial y component of the velocity. Okay, so we can take components as usual. You would have vx0 equals v0 cosine 50, which would be 35 meters per second, cosine 50, which is 22.5 meters per second. The initial y component of the velocity would be v0 sine 50, which is 35 meters per second, sine 50. And then substituting into your calculator, you get 26.8 meters per second. So we can take these and put them into the figure. All right, now I've got you started. So pause the video and see what else you can fill out without getting started on the computations just yet. Okay, let's see what else we can fill out. So we're going to assume that we launch at time 0. We're going to assume that we launch from the origin. Now, at moment 1 here, one thing we can figure out at moment 1 is the y velocity at moment 1. Now, to get the y velocity at moment 1, think about that red flashlight concept I've mentioned in the previous videos and over here. Think about that projectile is carrying the red flashlight, which makes a spot of red light on the y-axis. And think about what that red spot would be doing as the projectile traces out its trajectory, right? That red spot would do like this, and then like that. And can you see that at that moment that the projectile reaches its maximum height, that red spot over here reaches its maximum height as well, turns around, and then starts to come back down. So can you see that at this moment, that red spot has reached the top of its, quote, motion, which means that the velocity of the red spot at this moment is 0, which means that the y velocity of our projectile at this moment is 0. Let's put that in there. The other thing we would know here is the x velocity, because that is constant throughout. So we can put this in as 22.5 meters per second. At the moment the rock goes over the wall, we know the y component, y2, that would be 30 meters, because we are given that the wall is 30 meters tall. Other than that, we can just put in that the x velocity is still 22.5 meters per second. Now let's get to solving part A of the problem. And we are just trying to figure out now, what is this x2? What is this horizontal distance that we have set up between the catapult and the wall? Now, how are we going to get that? Well, let's go to the equations over here. And you notice that there's only one equation with an x in it. Here we're looking for x2. I've written the equations over here so that they connect moment 0 and moment 1. That's not a big deal. We can always change the subscripts to connect moment 2 to the other moments. Okay. But the problem here is this is our only equation which has an x in it. And in order to get that x, we would somehow need a delta t. We would need a time between the rock being launched and the rock going over. Now, we can't get that delta t from the x equation. We're going to have to use an analysis of the vertical motion to get the delta t. Now, there's two options here. One option would be to use equation 4, take equation 4 and write it so that you connect moment 0 and moment 2 to each other, and then you're going to have a quadratic equation in the time. That's one way to do it, and if you want to do that, you can pause the video and go right ahead and do it that way. The second option, which students usually seem to prefer, is a two-step process. In this two-step process, what we do first is we use equation 5 to figure out the velocity of the rock as it's going over the wall. Once we figure out the velocity of the rock as it's going over the wall using equation 5, then we can go to equation 3 to get the time. Now, I'm expecting that you're going to go with the second option because in most cases, that's what students pick. So if that's what you're doing, take equation 5, use equation 5 to solve for this velocity here. And I'll give you a hint here. Remember that the rock is going down as it goes over the wall. And then once you get this Vy2, then go to equation 3 and get that time difference. So pause the video, give that a shot, and then rejoin the video, and I'll show you what I do. Okay, so here we go. This is going to be a three-step process. First, we're going to use equation 5 to get the velocity of the rock as it goes over. Then we're going to use equation 3 to get the time from moment 0 to moment 2. Then we can use equation 2 to get the x coordinate here at the wall. All right, starting with equation 5, we are writing it so as to connect moment 0 to moment 2. That gives us Vy2 squared equals Vy0 squared plus 2ay y2 minus y0. Y0 is 0. Everything else we have to plug in. Now we're going to take the square root, and here it is important to remember that we have both a positive square root and a negative square root. So put in Vy0, 26.8 meters per second squared, plus, and then 2ay was minus 9.8 meters per second squared, and 30 meters. And take the square root of the whole thing. Now that value you get from punching all this into your calculator is 11.4. Now you're taking the square root of meters squared over second squared. That gives you meters per second. Okay, now do we want the positive square root or the negative square root? Well, we want the rock to be going down as it goes over the castle wall, because that's what gives us the most distance between our catapult and the castle wall. So let's take that minus square root. So Vy2 is minus 11.4 meters per second. Let me squeeze that into the paper here. Okay, so that was the first step. Step 2, we're going to use equation 3, writing it so as to connect moment 0 to moment 2. That gives us Vy2 equals Vy0 plus ay. And since we are going from moment 0 to moment 2, delta t becomes T2 minus T0. T0 is 0. So let's isolate the T2. Take Vy0, move it to the left where it picks up a minus sign. Bring ay down into the denominator. Okay, so now let's flip sides and make our substitutions. Vy2, oops, I forgot the minus sign there. Okay, so Vy2 minus 11.4 meters per second minus Vy0, 26.8 meters per second. Ay minus 9.8 meters per second squared. And I get here 3.90 seconds. Okay, and I will leave the unit checking here as an exercise. So let's take that 3.90 seconds, put it into the figure. Now we go to the next step, which was to use equation 2, connecting moment 0 to moment 2, and use that to find the x-coordinate of the castle wall. All right, so I need to flip that sheet over. We have some clean space to work with. Okay, using equation 2 now, we have x2 equals x0 plus vx0 t2 minus t0. x0 is 0, t0 is 0. And finally, we get our answer to part A. X2 equals Vx0, 22.5 meters per second, times time 2, 3.90 seconds. And I get 87.7. Seconds cancel seconds, and the unit of the answer is meters. Okay, so we have solved our First part. Now we can go on to part B. And I think it may be easier to just rewrite what part B was, which was to find the maximum height of the rock or the projectile. In other words, part B is asking for y1. Y1 can be solved for in a single step, so pick the correct equation that connects moment 0 to moment 1, so that y1 is the only unknown. Take a shot at solving for y1, and then rejoin the video. Okay, so to solve part B, we would use equation 5 as written, connecting moment 0 to moment 1. Vy1 is 0. Y0 is 0. So to solve for y1, take the Vy0 squared, move it to the left where it picks up a minus sign. Divide through by 2ay, and we have solved for y1. Let's flip the sides now. We get y1 equals Vy0 squared, minus Vy0 squared over 2ay, thus minus 26.8 meters per second quantity squared, divided by 2, and then minus 9.8 meters per second squared. And here I get y1 equals 36.6. And I think we've seen unit checking like this before, so I will leave that as an exercise as well. But we get meters, which we would expect for a y coordinate. The last part of the problem is to find the speed of the rock as it goes over the castle wall. And this is just another exercise in connecting the components of the velocity vector with its magnitude. So let me just take this information here and copy it into a new figure. So x-axis, y-axis, let's put in our velocity vector according to these components. Here's our final velocity vector. Let's call that v2. Now let's put in the components. This would be our vy2 here. This would be our vx2 here. The magnitude of the velocity vector is the same as the speed. So we can say that v2, the speed of the rock as it goes over, is vx2 quantity squared. This vy2 quantity squared square root. And substituting 22.5 meters per second quantity squared plus minus 11.4 meters per second quantity squared square root. Okay, put all that into your calculators. I got 25.2 meters per second. And now we have completed a second example problem involving a free-falling projectile moving in 2 dimensions.